Okay, we come to a new part, new subsection, that's called borrowing capacity, the equity multiplier. And this is actually an extension, or rather an alternative to the original model, to the first model. An extension would mean that the original model is a special case of the new model. This doesn't apply here. It's just a different version of the model. And what's different is that in the old model, we had assumed that the investment had a fixed size of I. Okay, it couldn't be changed. So that would mean that the return to the where is here insert page um, insert page the return to the investment. Oh, now I still have the green color. It's look like this. We invest. Now this is the investment size. So I call it I. Okay. And in the old model, there was a critical value of I0. If you invest less than I0, then you get back nothing. Okay, so the function would look like if you invest less than I0, then you get nothing. If you do invest I0, then you get some return R with probability PH. And if you invest more than that, again, you get not anymore. You can put more money into the project, but it doesn't help you. So this would be the return structure of the project depending on the investment size I. Now, the assumption is a new assumption that the more we invest, the higher is the expected return. Could look like something like this. We get we invest something and we get proportional returns. So there are constant returns to scale. One potential, so I can write that up. Constant returns to scale. Okay. Which of the two assumptions would you think is more realistic? That's always a question that I ask the students when I meet them in class, which is not the case here. So I can still ask you, and and the answer was typically varied. And I would say that most realistically, I'll do that in green, would typically be something in between. For example, decreasing returns to scale would look like this. You see, it's a little, in the first part, it's more like the purple curve. In the second part, it's closer to the orange curve. So therefore, we kind of have two extreme cases, and the decreasing returns to scale case would be somewhere in between. Or it could also be that the more realistic case would would be something below a certain investment, you get nothing. But then if you invest, you get something, but then it decreases, something like this. So there is some minimum I min, and if you invest less than that, so that would be like a fixed cost. If you invest less than that, you get nothing, but above that, decreasing returns. Anything like that. And again, you see the realistic cases are somewhere in between. So why don't we discuss the realistic cases right away? Why do we start with these crazy, more unrealistic cases? Well, I would say the reason is because they're simpler. And if we want, then we can, as a next exercise, try to combine the two and then see what we get. And then see whether we get any new insights. Okay, so let's talk about the model. Here we go. What do we have? We have an investment of I. Well, it's now important to remember that in the past, the I was a fixed variable. Now it's a parameter. Okay, so it's endogenous. Okay, and it yields R times I in case of success and 0 in case of failure. Now there's another. It's just a notational difference. In the old model, the R was a variable that was measured in euros, in money, and now it's a factor. Okay, so in the old model, I could have been equal to 1 euro, and the R could have been equal to 2 euros. And now the I is just an endogenous number, and the R is a factor, for example, could be 150% or something like that. Has to be larger than 1, um, that you will see in the assumptions. The private benefit of the borrower is equal to B times I. So there is an implicit assumption here, and that's something that's very interesting for you to learn, that very often when we write something up mathematically, there are implicit assumptions in the making some choices. For example, here we choose we make the modeling assumption that the private benefit is proportional to the investment size. Well, is that realistic? That depends also um, on the interpretation. If we assume that the B is kind of the effort that you have to put in the project, or the effort that you save if you don't work for the project, then it depends. If it's like, if you have the B means that you work on a first idea, and once you have the idea, then you can change the scale without any additional cost. Then this B would not be proportional to the project size, so then it would make no sense to multiply the B with the I. But if you, for example, produce some goods, and on each good that you're producing, you have to work hard to make it. So it could be some mechanical parts, and each ones you have to polish to make them fly. In that case, the B would be proportional to the amount of stuff that you produce. So that would also mean proportional to the investment size. Okay, right. It's an assumption, and we can try to change this assumption in an exercise if we want. We don't have to try all kinds of exercises, but this would be one that we could try out. Okay. What else do we have? The borrower has initial cash A and needs to borrow I minus A. That's the financing gap. The A is not proportional to I because A is given. That's the amount of money that the investor has. And of course, it does not depend on how much he wants to invest. I mean, that would be nice. If you have bigger dreams, then you also have more money in your pockets. But that's, of course, not the case. So A is just a fixed number. Two more assumptions. One is that you have a positive NPV per unit of investment if you behave. So if you invest 1 unit of money, you get back 1 times R with probability PH, and this should be larger than unit of investment. Otherwise, the NPV it would be negative, and then there would be no investment in the first place. Then neither the entrepreneur nor the investors would like this positive and negative NPV project. But if you shirk, then the NPV is negative, even if you take into account the B. That's the same logic as before. Okay, so 1 is larger than PL times R plus the B. We could write that would be equivalent, but would be a little bit more intuitive. Instead of the first one, we could write PH times R times I is larger than I. And for the second one, we could write I is larger than PL times R times I plus BI. And then you see the I cancels out, is factored out immediately, and then the equations that we see here apply. And then we have one more assumption, and that is a little bit more difficult. And we can talk about what this assumption exactly means maybe later on when we've already been a little bit of the discussion of the model, because then it's easier to understand how it can be interpreted. The NPV that's pH times R minus 1. The NPV should be smaller somehow in comparison to something that's related to the moral hazard problem, because you see that on the right-hand side we have some B over delta P, and that's always standing for the moral hazard problem. Okay, so that's already the new model. So that's our, say, step one. Step one will always become shorter because most of the model we already know. The time structure is the same. Most of the model is the same as before. So therefore, introducing the model always becomes shorter. Now we have the first condition that we have to think about, incentive compatibility condition.